Anyway, it's a really pleasure for me to introduce our lecturer for this class. That yesterday I talked to you about sort of not really networking, but as you look around, the guys next to you, what's going to happen to you 20 years from now, and something your relation. So me and Professor Matalon went back a long, long time, and we were both junior faculty members at Northwestern University at that time. Yes, he was there and I was there, and it was really a great time in the 70s. You guys are too young, many of you. But in the 70s, it started from late 60s and 70s, and there's this big movement in developing a theoretical combustion. You started from Lignon, he's doing that, and then Sivashinsky, and then Professor Matalon, and there's Buckmaster and all that really developed the foundation of theoretical work. I touch a little bit, but I'm not as smart as he is. And but anyway, I try to come, based on the great theory, I try to do experiments to verify the theory and all that. So it's really a very, very wonderful time. So Professor Matalon has been whatever you want to call it, a giant in theoretical combustion throughout the times. And in the 80s, the theory of stretch flames, differential diffusion, came from him. And that's now the foundation of flame theory, a lot of it. And then, but he just kept on moving more, and lately been doing turbulent flames and all that. Those are not easy. So again, as I mentioned, that the summer school, I started out with just always have two courses, very important. Foundation, what I call foundation course. Combustion theory, that's the physics and fluid mechanics of it, and now combustion chemistry. You guys have to know it, okay? And the reason why I did it, I think I mentioned to you, because I realized throughout my career, these two, they're like water and oil. People in chemistry, they're allergic to fluid mechanics. People in fluid mechanics, they're allergic to chemistry, okay? But so we're stuck, right? You have to do it. So that's how I say I'm gonna have this summer school to sort of at least get you guys to know the important points of each. So this is the sort of the half of combustion, combustion theory. And again, it's really a great pleasure and honor for me to introduce to you Professor Matalon.
Thank you, Ed. Thank you for the introduction, and thank you all for coming here. I will say a few words about where I come from, where I started, and then we will start with the course itself. So I come from the University of University of Illinois at Urbana-Champaign. This is a picture of the College Hall. Urbana-Champaign is a twin city located about 130 miles from Chicago, south of Chicago. And it's essentially more or less is two cities that are built around the university, which was founded in 1867, so soon 250 years. I got my undergraduate education at Tel Aviv University in mathematics and physics. My PhD in mechanical and aerospace at Cornell. I spent 2 years at what used to be called the Polytechnic Institute of New York. Now it's I think, what is the name?
Camden School of Engineering.
Okay, it's connected to NYU. And I was in the Farmingdale campus, but I think I taught one course in combustion in Brooklyn on J Street, which is the big campus today. I spent 26 years at Northwestern with joint appointment in the engineering sciences and applied mathematics and mechanical engineering. And I moved to Illinois in 2007 in the Department of Mechanical Science and Engineering in the College of Engineering. And why combustion? I don't have to say much about it. It's all self-explanatory. Fire, pollution, energy, transportation, space, metallurgy, health, explosive, cooking, heating, everything is related to combustion. My interest is theoretical combustion, or the theory of combustion. But the ultimate is to predict a combustion system. That's what we all are interested in. And we need for this, obviously, experiments where we observe the combustion behavior. We need simulation to try to explain or predict mathematically or computing what we observe. But we mostly need theory in order to understand. And they are all, of course, connected. From the experiment, you observe things and you need to explain them. You need the theory. And the theory is usually compromised on many aspects of the physics. And you need simulation to quantify these things. And of course, you have to check your simulation against the experiment. And you have to see if they explain the theory. I have to, it would take me some time to know how to play with this thing. Okay, so the next thing is about theory. Just few words before we dwell into the subject. The mathematical description of a combustion system, as we will see in the next hour or so, it's rather complex. It contains of a coupled system of partial differential equation, highly nonlinear, and none of these equations, even in the simplest form, have exact solutions. And so we need to do some simplification, and that's where the theory comes. It's based on simplified model, where we remove some of the physical details, but we retain what we believe are the most important things. Again, the idea is to promote understanding. The theory provides often analytical expression of key combustion characteristics, as we will see, for example, a simple expression for the laminar flame speed or things like that. It's based on approximation, clearly, which lead to either exact solution, but this is rare, and so very often those are equations that we can solve numerically, but much easier because they don't have the full complexity that the general equation has. Incidentally, in fluid mechanics in general, when you reduce an equation to an ODE, it's considered as to be an exact solution in some sense. And so here, of course, it would be the same. The theory provide the the simplified model provide full parametric dependence, whereas very often in simulation you solve a problem for given condition, given temperature, given chemical setup, and so on. In a theory, you can allow for all the parameters to be free and examine them from one end to another. It identifies key physical mechanism, or the cause and effect of different things, so at least that's the attempt. It helps to explain experimental observation, and there have been many circumstances where the theory have guided the experiment or suggested experiment to be done because the theory predicted things that the experimentalists say, let's see if that can be also observed in the lab. It provides useful correlating experimental data, and it clearly it can be used to validate numerical simulation where you test your code on simple cases where you know there is an exact solution. And so, well, the next thing was intended to be a little anecdote, so I wasn't sure I will keep it or not, but I will put it anyway. It was in installing the streets of Paris, I saw this, this little sign, and I used my iPhone to take a picture of it. And what it says is the following. This is my own translation, but it's more or less exact. The theory is when we understand everything, but nothing works. The practice, meaning applications, when everything works and we don't know why. And here, and I'm not sure what it was meant here, because that was just in a little store, it's where we have succeeded in both nothing works and nobody knows why. So now let's move on with the content of the course. First of all, this is a tutorial. In other words, I'm going to start as if you know very little about the subject or nothing, and I will develop it, starting today with the governing equations and moving on to aspects of thermodynamics and chemical kinetics that you need in order to establish the full equation that describes the combustion process. And then tomorrow we will move into premixed deflagration, detonation. We will discuss the difference between them, the structure of a detonation wave, the structure of a premixed flame, and we will talk about ignition and extinction. And then the following day, we will mostly talk about flame instabilities. First of all, hydrodynamic consideration. Mostly will be on premixed flame, and stretch flame and flame instabilities. We will continue with that then with lecture 10 on the flame instabilities, and talk later on diffusion flames. And then the last day we'll talk about combustion of condensed phase, droplet combustion, and spray combustion, as well as turbulent combustion. I just want to say up front that there are the notes that are in front of you, or the printed notes, where they've been revised if you have seen any of the notes of previous years, and also I have changed or modified some of the topics, but unavoidably there are typos, and I know I've seen them already when I was going through the notes in taking a look how to prepare the lectures. And so I apologize for this. Some of those typos I may find out as I talk. Some of them I may not, but this is sometimes unavoidable, but you know, they exist. Second comment I want to make is that if you have any question, I want to keep this informal, so please raise your hand and ask questions. I'm sure that I have more material than I can cover, so sometimes I will move a little fast or maybe skip here and there certain things, but if you have any question, just don't hesitate to ask. So we should start with the first lecture on the governing equations. And the first thing that we're going to do is we're going to just quickly go through simple discussion of fluid mechanics of a pure substance and slowly add to it, or then in comparison with this, deal with fluid mechanics of a mixture. So the first few things will be just a discussion of the governing equation of a pure substance. We start with the conservation equation. We assume that the fluid is a continuous and homogeneous. So the structure of any subdivision, a small subdivision, is the same as the structure of larger samples. So we often talk about a fluid particle. A fluid particle contains many, many, many molecules. It's not on the molecular size, but it's small enough that it can be treated as using calculus as a differential or a small quantity. And in fluid mechanics, there are two ways to describe the motion. One is what is known as the Lagrangian, and the other one, which is due to Lagrange, of course, and the other one due to Euler, which is known as the Eulerian. The Lagrangian form is when we follow the individual particle. So it's like dynamics. We follow the fluid particle, and we know the position, we take a derivative, we know the velocity, we take a derivative, we know the acceleration, and so on. The Eulerian, we fix attention in space, and we ask what's going on in that volume in space, and clearly at different times there are different particles that go through. And so one of the first question would be how to relate these two things. And so if we take a certain quantity phi, for example, a fluid property, let's say density or temperature, and of course at a given point it's a function of the position and in time, and if we calculate the total differential or total change in that quantity. Yes.
We keep hearing that. I hear it on every time it's beeping.
Oh, it's this thing. Is
that microphone inside. Oh, you know what? That's probably what it is. If you could take that the mic.
oh, this
Or turn your volume down.
okay? Are we okay? Thank you. So if we focus, is that the beep? It's related to this.
Try now. Good?
Now we're good. Okay, so if we focus on a quantity phi and we take the differential, clearly we would have to take the derivative with respect to time and with each of the three coordinates. So the derivative with respect to time is going to be essentially the partial of phi with respect to time plus the x dt, which is the x component of the velocity, d phi dx, plus dy dt, which is the y component of it, etc. So what we form here is the dot product of v dotted with the gradient of phi, and together with the partial with respect to time is known as this is essentially the total derivative or the total change of phi, and it's known typically as the convective or the material derivative. You know, it's a derivative following a material. So if I'm asking what's the time rate of change of the temperature of a fluid particle, it's going to be the d capital, usually we use capital D by dt, so it's going to be dt by dt, which is dt dt plus v dot grad t, right? So this can clearly be applied to any fluid property, whether a scalar or vector. So this is, for example, the time rate of change of the density of a fluid particle, and this will be the time rate of change of the velocity of a fluid particle or the acceleration of a fluid particle. So we can easily now write equations for the conservation of mass, momentum, and so on, of a control volume which is made of the same fluid particle. In other words, when we follow that same fluid particles, because then the conservation of mass is just said that the total time rate of change of that volume is zero when no mass is created inside that volume that you are following. You are following all the time the same fluid particle. The same thing is if you write your conservation equation for the momentum. It's going to be the time rate of change of the total momentum of that volume is equal to all the forces which are acting on the volume, and these consist of the body forces, which is things like gravity or electrodynamic forces, whatever is acting on the entire volume, plus the forces which are acting on the surface of the control volume due to frictional forces or traction between one control volume and the neighbors. The surface forces are described by the stress tensor, which is a tensor containing essentially a matrix of 9 quantities, sigma ij, but due to equilibrium consideration, the tensor must be symmetric so that sigma ij is equal to sigma ji, and therefore there are only 6 independent quantities. And when you dot it with n, you get the force which is acting on the surface of that volume. The body force is described by this function f, or this force f, which is essentially the force per unit mass. Like if it was gravity, it would be the gravitational acceleration g. So we have written mass conservation, momentum conservation, and similarly, we can write an energy conservation, which is conservation of what I refer to as the total energy, ET, which is both the internal energy, E, and the kinetic energy, V square, essentially, right? V dot V, it's the kinetic energy. And the time rate of change of the total energy is equal to the energy, the rate of work done by the external forces, both the body and the surface forces, and those are expressed here. The body force over the volume V and the surface force over the surface S that consist of the volume, that cover the volume, and the rate of energy in and out of the control volume, which is described by the heat flux vector Q, which is taken to be positive for outward transport. So this is a total statement of energy conservation. And if we now use the divergence theorem, we can rewrite the, if we use the divergence theorem, we can rewrite the surface integral as a volume integral, which would be the divergence of that quantity. So just it's a rewrite of the previous statement, that's all. That's why this one is framed and not the other. So the main question is now how to express the time rate of change of a mass of a fluid which is fixed, not moving, right? Not that consists of the same material. So for that, we need to know how to take that, the differential or the derivative of a quantity where the volume V is changing, it's moving. For any quantity phi. In other words, what we need is a generalization of what is known in calculus as Leibniz theorem. We need the multidimensional analog to Leibniz rule of integration. Leibniz rule of integration tells you if you take a derivative of a quantity where the limits of integration change, say, in time, and you want to take the time derivative of this integral with respect to x, well, it's then you can move the d by dt inside, but then you have two additional terms that come from the boundaries, right? How does the boundary change? The analog to this in 3 dimensions is written here. The time rate of change of the integral of this quantity phi over the volume V, it's the time rate of change of what's inside the volume, plus essentially the flux in and out. And the flux in and out is calculated simply here. V dot n times delta t is that distance. It's like the volume in this little grid area, and you multiply it by ds throughout the whole surface. And so this is simply a kinematic relation. It's nothing to do with the law of fluid mechanics at all. And it can be applied to any quantity which is moving at some velocity v. Now, when the velocity v is the fluid motion, we refer that to as the Reynolds transport theorem. Okay, so Reynolds transport theorem is essentially is a generalization or is a statement of that general law that I stated. Now, the reason we need this relation, it's because, as you just recall a few minutes ago, all the conservation law were written as d by dt of a quantity of integral is volume v, and what we need is to apply this rule to all these three conservation statements. Oh. So before we do that, let me just also say that we can write Reynolds transport theorem in several ways. The one that I just wrote to you before was the one on top here, right? Which was the integral over the volume plus the fluxes. Another version is to use the divergence theorem and to replace the surface integral as the divergence, and then you can write it in this form, and that's the one that we will be using most soon. And another way to do that, another way to write this is to use the fact that the divergence of a product, there is a product rule, and so when you split this, you have a term which is v dot grad phi, which forms the total derivative or the material derivative. So any of these form is equivalent. But we are going to use the one which is there in the frame, then I wrote it on top. So now if we apply this to mass conservation, so what we need is to treat or to apply this to the density rho. And so apply that to the density rho, we see that the time rate of change of the mass of this volume, which is now fixed, right, is equal to d rho dt plus the integral of that plus divergence of rho v directly by the application of Reynolds transport theorem. And since that must be equal to 0, then the integrand must be equal to 0, because that's true for any differential volume dv. So the continuity equation or conservation of mass in differential form can be written in this way. And of course, there are several other ways that we can express the conservation of mass. If we again use the multiplicative law that I mentioned before, then this becomes d rho dt plus rho divergence v, and that's another form that we can write the conservation of mass. Incidentally, if I denote by capital V as the reciprocal of the density, which will be what we often refer to as the specific volume, then you can rewrite this as then what you will see is that the divergence V, well, it's a rewritten of this equation. It's 1 over v dv dt equal to divergence V, which means that divergence V is essentially the rate of compression or dilation. Another comment to make is that if the change in density is small, then this first term is negligible, and therefore the divergence V is 0, and we refer that to be as an incompressible flow. Okay, so we move on now to conservation of momentum, and I'm going to do these a little faster, but essentially I want to just give you the idea. So here is the statement that we made before about conservation of momentum, and what we want is apply Reynolds transport theorem to this term. You essentially take the time derivative or the material derivative of this quantity of the momentum. And so we do that by using the transport theorem. You see here are the first two terms. And then the remaining two terms are the body forces and the surface forces can be by the use of the divergence theorem written as the divergence of sigma. And so we end up with an integral, which is the integral over the volume, okay, of a control volume, a small control volume. And since that is equal to 0, then clearly the integrand is 0, and the integrand can be written in that form, which is the first two can be simplified to simply rho dv dt by the use of the continuity equation. In other words, the continuity equation will give you v times d rho dt plus v times the divergence of rho v, which is 0, and the remaining is what is left on the left-hand side. So it's a simple statement that if you follow a fluid particle, the mass times the acceleration is equal to all the forces, namely the body force and the surface force on the fluid particle. But this is the differential form of the momentum equation. Similarly, we go to the total energy equation, and with similar steps, we end up with the differential form that tell us that rho d by dt of the total energy is the work due to the body force, the surface force, and the heat transfer in and out or the fluid particle. It is customary to write the energy equation without the kinetic energy. And so what you want to do is to remove the kinetic energy part. And to do that, it's very simple. What you have to do is to dot or to multiply the momentum equation by the velocity v. So then you have a quantity d by dt of v squared. The 2 is just simple from the product. And so the time rate of change of the kinetic energy turn out to be those two terms, okay? One of them related to the work done by the body force plus some contribution from the surface forces. And when this is subtracted from the total energy, you get a statement for the time rate of change of the internal energy. The difference between these two quantities, which, by the way, they are both, it's essentially scalars, because what you have, it's a tensor dotted with a vector, which is a vector, and take the divergence of a vector, which is a scalar. Same thing with this quantity. These two terms represent what is known as a contraction of the two tensors sigma and grad v. The first one is sigma, have component sigma ij. The second one is dv I dxj. And so this is essentially a summation over I and j. Here we have used the summation convention. So it's I appear twice, and so you sum over I. J appear twice, and so you sum over j. So that's a double sum and gives you a scalar, which is essentially the energy dissipation. So what you have here is rho times the EDT is equal to this energy dissipation and the heat transfer. And we are going to further discuss or simplify these equations. So so far we have statement of conservation of mass, momentum, and energy. And what we need is constitutive relation that tell us, that complete this equation, tell us what is the stress tensor, how it's related to the fluid quantities, and so on. So the first constitutive relation, by the way, there is a difference between the constitutive relation and the law or the conservation law. The conservation laws are laws of statement that mass is conserved, momentum is conserved, energy is conserved. The constitutive laws are essentially a relation that are taken from experiment, that are taken from just experience. So for the relation between the stress tensor and the strain what we adopt is the simple linear relation, and this is known as Newtonian fluid. There are fluids that don't obey that law, and they are referred to as non-Newtonian fluid. So for a Newtonian fluid, sigma, the stress tensor, can be written as the pressure P times I. I is an identity tensor. So this is essentially the mean of the normal stresses, the stresses that appear in the diagonal of the stress tensor, plus the viscous stress tensor, the contribution due to the viscous stress. And the viscous stress can be related to the strain tensor, which is grad V plus grad V transposed, and plus another quantity which is related to the compression effect, which is related to the divergence V multiplied by, again, the unit tensor. And you see that in this relation there are two coefficients. One of them is known as the shear viscosity mu, and the other one is the bulk viscosity kappa. And so the relation, again, for a Newtonian fluid involves these two coefficients, and then that the relation is expressed here, where this capital sigma is the viscous stresses. So if we substitute that into the momentum equation, then what we have now is that the time rate of change of the momentum is the gradient of the pressure, and the viscous contribution, and then whatever was before from the body forces. Before moving on to the, remember in the energy equation we had also this contraction that appears. So since we have in front of us now the functional form of the stress tensor sigma, well, all I wanted is just to produce this contraction, and when you produce this contraction you obtain that it's equal to minus P times the divergence of V plus a function phi which is written here in components, and this is known as the viscous dissipation function, which I will rarely use in detail, and therefore I will always keep it and call it as phi. Okay, so this is one of the constitutive relation that we needed in the equation. The second one that we need is something that tells us what about the heat flux Q. And the heat flux Q is, we assume for that Fourier law of heat conduction. Again, that's taken from experiment or from knowledge of the behavior of certain fluids. And so it's assumed that the heat flux vector is proportional to the gradient of the temperature. In other words, heat flow from high temperature to low temperature, and the coefficient of proportionality lambda is known as the thermal conductivity, and it's a material property. So if we substitute this for the divergence of Q, which was here, by the way, the minus is clearly because the heat flux is from high to low temperature, right? And so if we substitute that in this in the energy equation, so we are replacing the Q with the divergence of lambda grad T in general. Okay, so these are the two things that we come up with this constitutive relation, but we still have other unknowns in the equation. For example, we introduce temperature. So how do we relate temperature to the other variables? We introduce pressure. How do we relate pressure to? So for this, we need thermodynamics. For a pure substance, we know that the state of a gas is uniquely determined by two variables. In other words, in thermodynamics, if you take one quantity P, for example, the pressure, it's related to the density and temperature, or to two other quantities, if you like. But normally in fluid flow, what we relate pressure is to density and temperature. Same thing with internal energies, we're going to be function of pressure and temperature. There are other functions that are used, other thermodynamics functions that are used in our derivation of equation or in writing equation. One of them is enthalpy, and everything is per unit mass here. So H is the enthalpy per unit mass, which is equal to the internal energy plus P divided by the density. Often you refer to that PV, but V is the specific volume, which here I don't want to introduce that term because I'm not going to be needing it. So I will keep it as 1 over rho, which is the density. Another relation, another thermodynamic relation is the entropy, which can be related, which is S, right, per unit mass, and it can be related to any of the other functions that I have mentioned by one of those two relations, often known in thermodynamics as the TdS relation. So this one make relation to the internal energy, pressure, and density, and this to the enthalpy and pressure and density. Okay, very often we assume that the gas or the fluid is an ideal gas. And so for an ideal gas, there is a simple relation between pressure, density, and temperature, which is written here, P equal to rho RT divided by W. R is the universal gas constant. It has this value in those units. And R and W is the molecular weight of the substance. So if you are often rewriting this as rho RT, the R is just the specific gas constant, which is the universal gas constant divided by the molecular weight. Another special property of ideal gases is that the internal energy and hence the enthalpy are a function of temperature only. And so E is a function of temperature only. And you see H being defined as E plus P over rho will also be, because E is a function of temperature only, and P over rho from the equation of state is proportional to temperature. And so H is also a function of temperature only, which which suggests to define what we refer to as specific heats, Cp and Cv, which are essentially the derivative of H or the derivative of E with respect to temperature. So the H dt is the specific heat at constant pressure, and the E dt is the specific heat at constant volume. These are not necessarily the definition of these quantities in general, but certainly for ideal gases, it's true. There is, of course, you can integrate this expression and write that H is the specific heat at some reference temperature T naught plus the integral of the specific heat Cp dt, right? And the same thing with E. Now, when we deal in gas dynamics of a pure substance, we often don't care about the reference value because we are interested in just the change in the enthalpy or the change in internal energy. That is not true in combustion because there are many species, as we shall see, and so we have to adjust the reference to be something that we refer everything to it. And so we are going to see that that's an important thing to do, which essentially is the source of what we call heat of combustion, right? So that will come soon. It's another relation which is important to note is that if we take the definition of H, which was H plus E, H equal to E plus P over rho, and we differentiate it with respect to the temperature, we see that there is a relation between Cp, Cv, and this is just the gas constant, or the specific gas constant. And so Cp is always larger than Cv because R is positive. Another quantity that we often introduce is the ratio of specific heat gamma, which is Cp over Cv. And since Cp is larger than Cv, clearly gamma is bigger than 1. Here are two relations that we often use. Instead of the gas constant, we prefer sometimes to bring in Cp and the gamma. So we replace R over W by Cp gamma minus 1 over gamma, and the same thing with Cv. Now, very briefly, I have introduced here lots of, one more thing. There are different forms that we want to write the energy equation. One of the form was with respect to the internal energy, which I did before, but sometimes we want to express it in terms of the enthalpy. And so express it in terms of the enthalpy is just using the relation that H is E plus P over rho. When we differentiate this relation, we take the convective derivative or the total derivative, then and then I multiply by rho because there's a rho here. So rho dH dt turned out to be rho dE dt plus the derivative is P, dP dt, the rho cancel, and then the derivative of rho, which is 1 over rho squared d rho dt and 1 over rho cancel. And this, well, minus clearly because it's 1 over rho, the derivative of 1 over. And this quantity is exactly the divergence of V from the continuity equation. So essentially what you get here is the PdV cancel, right? This term and this term cancel. And you end up with rho dH dt is dP dt plus the viscous dissipation function and the heat transfer term, right? So there are the two different forms of writing the energy equation. Another form is in terms of entropy. So if we use this function, this relation, or which you can view as a definition of the entropy per unit mass, and you again take the total derivative, you find out that this term dP dt cancel, and so what you end up is rho d by dt of the entropy is 1 over T multiplied by the viscous dissipation minus the heat transfer, which in fact it's a nice way to observe a statement of thermodynamics. One of them is if you have a reversible process, namely that phi is equal to 0, then delta S with the change in enthalpy is going to be proportional to the heat acquired divided by the temperature, right? If in a reversible transition from one equilibrium state to a neighboring one, there is the increase in enthalpy then is proportional to the heat given to the fluid, which is just that statement. Another thing that you can easily see from this expression, that if you have an irreversible process where phi is clearly positive because heat is dissipated, then delta S will be larger than when you have the irreversible process. Okay, those are just side comments. The two last thing that I want to point out, that if you have an isentropic flow, namely there is no change in entropy, or the S is equal to 0. In other words, a process which is adiabatic and reversible, right? Both phi and divergence Q are 0. Then in addition to the fact that dH is equal to dP, in addition to, to the fact that dH is by definition Cp dt, you also have from the TdS relation that dH is dP over rho because ds is 0. And so from these two relations, you can eliminate the enthalpy and find out that for an isentropic process, P rho to the minus gamma is a constant, right? I am not sure if I will use this. I had that in some topics in my notes, which I am not sure I kept this time, but anyway, for generality, it's there. And the last thing that we will need, especially when we talked about deflagration and detonation, the speed of sound. The speed of sound is defined as the square root of the change in the pressure relative to the density of an isentropic process. So dP over d rho, dP d rho, when S is kept constant, can be evaluated from this expression, and it's clearly going to be equal to gamma P over rho, or if you use the equation of state for an ideal gas is gamma RT, right? So these are all the statements that I briefly, well, it took longer than I thought, but I wanted to make for a pure substance. What we have is conservation of mass, momentum, energy, which I wrote here in terms of enthalpy. And then it has to be supplemented by an equation of state, P of the ideal gas law, and a definition, if you like, or it's also a relation of state, which is a definition of enthalpy, which in this case is just Cp dt. What we have in this equation is one unknown, rho, three velocities, which is 4, pressure 5. This is all related to velocity, so this doesn't add anything. 5. The enthalpy, which is 6. And what else? I have one more I missed. And temperature, which is going to show up from the divergence Q. Maybe it's here, I don't know. Okay, so we have 7 unknowns, right? And we have, in fact, 7 equations. 1, 3, which makes it 4, 5, 6, 7. So we have 7 equations, 7 unknowns, a complete set. It's a closed set of equation, and it can be solved. The sigma here, remember we wrote an expression for it that relate to the basic variables, and the Q as well. So now what we want is really to generalize, or to do the same, to follow this set of ideas that I have presented here for a mixture that consists of many species which are different. So the first thing is we have to decide how we are going to use, what's the notation that we use, and what's the form that we use to describe the mixture. So let's say the gas mixture consists of n species. I identify them by the index I, 1, 2, 3 to n. This script mi is going to be the chemical symbol of species I. So for example, hydrogen, oxygen, and so on. Each is used the symbol M for it. What we need now is to describe something which identify, or quantitative description of the chemical transformation between species. And for that, we define one of the way to define is using the notion of concentration. So what is the concentration Ci of species I? Well, it's defined as the number of moles of species I per unit volume. So it's number of mole Ni divided by the total volume. And this is for all the species 1, 2, 3, and so on. Well, by definition, the Avogadro number is the number of molecules in a mole. That's essentially if you want to define mole, but let's move on with this. So we define concentration. What we can now is define the mass of Mi of the species I. So the mass Mi is going to be related to the number of moles Ni multiplied by the molecular weight of that species. So that's what Mi. Then we can now define the density, which is the mass of species I divided by the total volume. So this is rho I. That's the density of species I, only of the let's say the hydrogen in the mixture and so on, right? It's not the total density. Now, if we sum all the densities, rho I, which is the same thing as saying I sum all the masses divided by V, since V is common to all of them, it's a total volume. That's a total mass divided by the volume, and this is the density of the mixture. Similarly, we can also talk about the concentration of the mixture, which is the sum of all the Ci, which is going to be the sum of Ni divided by the volume. The sum of Ni is the total number of moles in the volume of all the species, and therefore that's the total concentration. If we know concentration and we know the mass, we can talk about a mole fraction or a mass fraction. So the mole fraction is going to be the concentration of species I divided by the total concentration, which is the same thing as the number of moles divided by the total number of moles. Clearly, that's a fraction between 0 and 1. And if you sum this over all I, you're going to get it's equal to 1, because the sum is Ci is C, and so that's sum to Xi. Similarly, the mass fraction is defined as the mass of species I divided by the total mass. So you can think of this also as the density if you divide both by the volume. So it's the density rho I divided by the total density. When you sum all the yi, right, the sum of all rho I is rho, so the sum of all the yi should be 1. And again, yi is clearly a fraction between 0 and 1. Okay, so these are the mole fraction and the mass fraction. There is clearly a relation between mole fraction and mass fraction, and the relation is written here. The mass fraction, the mass mi is equal to the total mass times the mass fraction, and this can be replaced by the number of mole times the molecular weight. And so you can write the total mass as the total number of moles times some molecular weight of the mixture, which I didn't define yet, but I'll define it in a minute, multiplied by yi. And so clearly the relation between mass fraction and mole fraction is related to, as you see here, xi, omega I divided divided by the total or the molecular weight of the mixture. So this is the relation between them. So how do I define the molecular weight of the mixture? So, if I start with the mass m and I sum for all I, mi, this is the same as ni times the molecular weight wi, right? And the wi can be written as, the ni can be written as n times the mole fraction, right? Xi. So, but this has the form as number of moles times something, so clearly that something would be like the molecular weight of the mixture. And so the molecular weight of the mixture is essentially the summation of mole fraction times molecular weight, okay? But if you use the relation between mass and mole fraction, you see that in terms of mass fraction, it's not a simple summation like this. Here, it's going to be yi divided by wi, which is equal to xi divided by w. And so what you see is that essentially this sum is equal to 1 over the molecular weight. So the molecular weight, which is the summation of the different molecular weights, but in proportion to the mole fraction that is in the mixture, in terms of the mass fraction is expressed as yi divided by wi, the reciprocal of that, right? Okay, so that's an important relation to note. Okay, now that we have a way to identify different species and we have defined the mole fraction and mass fraction, let's start with writing some balance equation. So the first one, I want to write essentially a mass balance for species I, for the mass conservation of mass, say, of species I. For species I, it's going to be d by dt of the density of species I plus the divergence of rho I vi, where rho I have written it here as rho multiplied by yi, right? And the same thing with here. And vi is the velocity of species I in that mixture, okay? It's not the total velocity, just the velocity of species I. Now, if this was conserved, it will be like from the conservation of mass, it will be equal to 0. But clearly, species I may not be conserved. It may be produced or consumed. And so on the right-hand side, we have a rate, which we still have to determine clearly, which is going to be the rate of production or consumption of species I. And so this is essentially the statement which is equivalent to conservation of mass, but when we focus on species I. Now, this introduction, I'm going to take a break in a few minutes after I do 2 more slides or so. So if we focus on species I, and we say that species I is moving at some velocity, think of those species to be, let's say, red and some other species blue, and each of them is moving at different velocity vi. We are interested in something which is the mass average velocity. And the mass average velocity will be the velocity v, which is mass weighted, or it's weighted by the amount of mass of that species, right, yi. So v is the mass average velocity. Now, if you have the bulk is moving at some average velocity and species I is moving at a velocity vi, clearly there is a relative velocity between the two, and this relative velocity is what we refer to as the diffusion velocity, which is denoted by a capital Vi. Note that all the bold faces are vectors, right? So capital Vi is the diffusion velocity. Now remember, the sum of Yi must be equal to 1, which means that if I take the sum of this expression here after multiplying by Yi Vi is going to be equal to the average velocity v, and v times the sum of yi, which is 1, is v, so v minus v is 0, and so that sum must be 0. So that's a statement essentially that the net diffusion fluxes is 0. Okay? That's one constraint which is important to remember, as well as, of course, this one. So the next step is to introduce the diffusion velocity and bulk velocity instead of the velocity of species I. In other words, that's not an unknown that we want to keep in our equation. We would like to replace that with the bulk velocity and a diffusion velocity. So if I replace the Vi here with that, it's just simple substitution. That's the expression we get. Clearly, the diffusion velocity Vi still need to be defined. In other words, we will need a constitutive law to determine that. If I sum all these equations for all I, since the sum of yi is 1, from here I get d rho dt. Similarly, using this this constraint, in fact both constraints, when I sum this expression I get divergence of rho v, and since the summation of omega I must be 0 because mass is neither created nor destroyed by chemical reaction, then the right hand side will be 0. Of course, we are going to come back to this when we talked about chemical reactions and chemical kinetics, which is going to verify that that's indeed the case. So the idea is that when you sum over the mass balance equation over all the I, you get the mass conservation of the total mixture, which is in the same form as for a pure substance. And just one more, let me see, yeah, one more one more thing about species conservation, and then we will take a break. The equation on top is what I wrote earlier, right? And I can split the divergence here again using the product law. The diversion of a product is product of two terms. And when you do that, then clearly this term, which is a total conservation of mass, is equal to 0, pops out as multiplied by yi. So what you are left with is the material derivative or the convective derivative of yi dt, the divergence of rho yi vi, which is the diffusion fluxes, and on the right-hand side, the production or destruction of species I. And you can write clearly n such equation for each species. However, since the sum of the n equation is equal to the conservation of mass, the total conservation of mass, only n minus 1 of those top equations are linearly independent. In other words, if you use both, you are counting something, you're using the same thing twice, right? So you can either use n-1 equation plus the total conservation or the total n equation, okay? Let's take a break. Of course, if you use the total conservation of mass, d rho dt, as one of your equation, the question is, how do you find the last species, right? Well, you find it from the sum of yi is equal to 1. In other words, one of them is an algebraic equation. I think the next thing is conservation of momentum, so let's take a break and then we will